Hello students. So in previous video we learned one dimensional Gaussian integral and we saw its two extensions. One was e to the power minus ax square and another was e to the power minus ax square plus bx. And the last one is called shifted Gaussian integral and we didn't derive that. I told you that you do yourself and verify it in next video. So today we will derive it and you will verify it. Fine. So after this, that's deriving that shifted Gaussian integral, we will shift to the higher dimensional Gaussian integral. So let us see. So this is actually the one dimensional shifted Gaussian integral. So how to derive this? We have to focus on the its exponential power. So its power is, if I make it in red box, this is the power. So I will make it perfect square or complete square, then you will see that it actually reduces to the basic Gaussian integral. So let us see. So e to the power minus ax square plus bx. You can write it like this: minus a, you take common, x square plus minus b by a x. Fine. So now you can make it perfect square and this integration can be written like this: minus a x square minus 2 b by 2a x plus b by 2a the whole square. Fine. And since you have added this term, you have to subtract this term also, so that the value of the power is same. Fine. Now what you can do, you write it like this. Fine. So this term within the parenthesis becomes perfect square, and which you can write like this: e to the power b square by 4a. Correct. So now what you can do is the change of variable so that it exactly look like a basic Gaussian integral, or you can say normal Gaussian integral, minus a z square e to the power b square by 4a, where you did the change of variable where z equal to x minus b by 2a. Fine. So now our the integration becomes e to the power minus ax square plus bx minus infinity to plus infinity dx. This becomes minus a z square dz minus infinity to plus infinity, and a factor e to the power b square by 4a comes out, the integration, which is constant. Correct. So, and you know the value of this particular integration because we derived it in the last video. So you can write it like this: e to the power b square by 4a, and the value of this is root pi by a. So yes, so it is derived. So the value of this integration, shifted Gaussian integration, one dimensional, is this. Fine. Okay. So here the condition is real part of a is greater than 0 and b is any finite complex number. Okay. So now we will look for higher dimensional Gaussian integral and we will start with the two dimensional. Let us see one integration. So if I write minus infinity to plus infinity dx minus infinity to plus infinity dy e to the power minus x square plus 2 nu xy plus y square. So if you are asked to derive the value of this integration, we will make it like a basic Gaussian, in terms of basic Gaussian into normal Gaussian integral. so that it becomes easier for us to derive it. So what we do here is we have taken out the factor e to the power minus x square outside the integration of y, because x and y are the independent coordinates, correct. So now we have minus y square plus 2 new xy. So this remains the same as it is, and we make it perfect square. So you can make it perfect square and do the integration, or you can use the previous shifted Gaussian integration formula to write the value of this integral. So if you compare it with the e to the power minus x square plus bx, so its integration is e to the power b square by 4a root pi by a, correct. So write the value of this integration here, and it will be root pi. So it is exponential, the power is 2 new x square divided by 4. So x is equal to minus x, so minus infinity to plus infinity dx e to the power minus x square, and this becomes e to the power new x square, and root pi factor comes out. So root pi times minus infinity to plus infinity dx e to the power minus 1 minus new square x square, correct. So our integration is root pi times minus infinity to plus infinity dx e to the power. So we did two kinds of extension in last video. One was the shifted Gaussian integral, and one was this e to the power minus ax square minus infinity to plus infinity dx. So what is the value for this? The value is only for root pi by a. Using this formula, we will write the value of this particular integral, this integral. So let us write that using this formula below given. You will write it like, so to write this, root pi by 1 minus nu square. So the value is pi by root 1 minus nu square. So this is the integration of a two-dimensional Gaussian integral. But if you see, this value diverges for nu equals to plus minus 1. Okay, so to understand why this particular integral diverges at these values, nu equals to plus minus 1. So let me first tell you, at nu equals to plus minus 1, this denominator becomes 0, and so this term become something divided by 0, which is infinity, right. So this integral is finite when nu is within minus 1 to plus 1. So at minus 1 it diverges, at plus 1 it diverges, and if you want to understand why this is happening, let us understand. So our integrand is minus e to the power minus x square plus 2 nu xy plus y square, fine. So suppose nu is equal to plus 1. In that case, this become fine and this become correct. So now for the value of nu equals to 1, our integration is e to the power minus x plus y to the whole square dx, and this is a double integration, dy minus infinity to plus infinity minus infinity to plus infinity, correct. Now let us do a coordinate transformation. So suppose we write u equals to x plus y, and y equals uv equals to x minus y. So we are doing here a coordinate transformation, correct? So if we do here this coordinate transformation, how will you write this area element in terms of du dw? You will write multiplied by some Jacobi factor. So in some previous videos I told you that how to calculate this Jacobi factor, correct? So for this kind of transformation, if you calculate this Jacobi factor, that comes out to be 1 by 2. So if you haven't seen that video, please go to the previous some videos where you will find. I will also put the link in the description where you can find the link for this video, where I have calculated this Jacobi factor for the for a kind of transformation. So for this kind of transformation, this Jacobi factor comes out to be this. So dx dy is equals to 1 by 2 du dw, correct? So the integration is minus infinity to plus infinity du, this is not dw, this is dv. So dv du, this integration e to the power minus u square, fine. So here you see that this du integral, this du integral is finite and its value is root pi, correct? So we saw this is the normal Gaussian integral which we have already derived in the first part of this chapter, okay? So now you see this integral where we have write minus infinity to plus infinity dv. So this is not finite, this diverges. So what you can do is like this, write like this. So you are doing the integration over a constant function which have the value 1. So you are going to add this number each time from minus infinity to plus infinity, and it will give you the some infinite number, fine. So this integral diverges for nu equals to 1. Let us go to the 3-dimensional Gaussian integral. So if you want to see a 3-dimensional Gaussian integral, I will write it like this: e to the power minus x square plus y square plus z square 2 nu xy 2 nu yz 2 nu zx, and then this is a 3-dimensional integration. So dx dy dz, correct? And the limits are from minus infinity to plus infinity for all kinds of variable, okay? So here you do the same as you did for the 2-dimensional Gaussian integral. So what we do here is that we make it something like this: dx e to the power minus ax minus x square minus infinity to plus infinity, this is dy, and you take outside this factor and you do this like this: minus infinity plus infinity dz, and you write it like this: minus z square minus 2 nu yz minus 2 nu zx, fine. So this part is shifted Gaussian integral. So how would you write like this? Fine. So you compare it with this type of integration and its value is, so you do that here and write this, the value of this last part of integration over z variable. So this will become root pi e to the power 2 nu y plus 2 nu x square divided by 4. So here is a 4a, correct? So we got this minus infinity to plus infinity dx e to the power minus x square. Similarly you write it here dy, you take the factor of root pi outside, e to the power minus y square 2 nu xy, and you write it here So this will become nu, you take outside common x plus y the whole square. Fine. So what happens here, you take two factor outside which cancel out with this 4 and we have this. Okay, so you can write it like this now, root pi minus infinity to plus infinity dx e to the power minus x square minus infinity to plus infinity dy e to the power minus y square minus 2 nu xy, and you write also plus nu square x square plus nu square y square plus 2 nu square xy, correct. So this is the integral now, right now. So you will write it like this, root pi minus infinity to plus infinity dx e to the power minus x square. You again make it like a shifted Gaussian integral so that you can write the formula of the shifted Gaussian integral here. So e to the power minus 1 minus nu square y square, this comes from this term and this term, correct, and you make other terms here. So other terms must contain y factor so that you can use shifted Gaussian integral formula. So that is 2 nu xy 2 nu square xy, and there is a term which is nothing but nu square x square, which you can take outside this y integral. So I can be written as root pi minus infinity to plus infinity dx e to the power minus x square, you take outside this factor outside, nu square x square, and the y integral become this, correct. Fine. So we have now shifted Gaussian integral formula, you use that. So this will become minus infinity to plus infinity dx e to the power minus x square nu square x square. This will become root pi divided by 1 minus nu square. Fine. And you write it like this, 2 nu square x minus 2 nu x the whole square divided by 4 1 minus nu square, correct. So here keep in mind that you shifted Gaussian integral is valued only when a is greater than 0, and what is a here, this is our a parameter. Fine. So 1 minus nu square must be greater than 0. So you do like, you take this factor outside so that it becomes pi by under root 1 minus nu square, and the integration is still remaining over x e to the power minus 1 minus nu square x square. Fine. Okay. So we have the integration remaining over e to the power, you write it like this, 2 nu square x square 2 nu square minus 2 nu, so whole square divided by 4 1 minus nu square. So we have, now you can use, you can more simplify this by writing it like this. Fine. So again you use this kind of formula, e to the power minus ax square integration. So what is the value of this, root pi by a. So you use this formula here and you write the answer like this. So if you want to simplify this, this can be written like this. So here this term become a parameter in our Gaussian integral formula. So you put it here, you can write it more simpler way here. So this term cancel out, this factor cancel out, and the integration becomes pi to the power 3 by 2, and you take outside this 1 minus nu square 1 minus nu factor come outside. So inside we are remaining with a term 1 plus nu square whole square and minus nu square, correct. So this will give you pi to the power 3 by 2 1 minus nu under root 1 plus 2 nu. So you see here, this is the value of 3-dimensional Gaussian integral. Fine. Yeah. So this integral, if you look, this integral also diverges for nu equals to 1 or nu equals to minus 1 by 2. This integral converges within the range minus 1 by 2 to 1. So nu equals to minus 1 by 2 and nu equals to 1 are the singular points. So this integration is valid within this range. So if you want to look why this is happening, if again you want to analyze that why nu equals to 1 and nu equals to half this Gaussian integral is diverging, if you want to look this, you can do again the coordinate transformation, like here u equals to x plus y plus g, v equals to x minus y minus g, sorry, plus, and w equals to x minus y minus g. So you do this coordinate transformation, calculate this volume element with this Jacobi factor du, dv, dw. So from taking the determinant and modulus of the Jacobian matrix, you get that this value comes out to be 1. So dx, du, dy, dw is equals to du, dv, dw. So in this way, the Gaussian integral for nu equals to 1 e to the power minus x square plus y square plus g square plus 2xy plus 2yz plus 2zx square. This Gaussian integral for nu equals to 1 become the perfect square in xy variables. So this becomes e to the power minus x plus y plus g the whole square dx dy dz, correct. So since we have done the coordinate transformation, this will become minus u square du, dv, dw. Since if you want to check whether these three are the independent coordinate or not, why we want to check whether these are the independent coordinate or not independent coordinate, because here we are doing the higher dimensional Gaussian integral. So we have to take care that these if u and v and w are the independent coordinate, then this integration can be written like this. If if u, v, w are not the independent coordinate, then you can't write LHS equals to RHS. So to check whether these are the independent coordinates or not, this u, v, w, because we have defined here some coordinate transformation, whether this kind of relation gives us independent coordinate or not, if you want to check it, what you can do is that write a u plus b v plus c w equals to 0. You write like this and put coordinate relation for u, v, w here, and you will find that a equals to 0, b equals to 0 and c equals to 0. So if it is so, then these are the coefficient a, b, c and are the coefficient of this coordinate u, v, w. So if any combination of coordinates, any linear combination of coordinates is giving us 0. So if it is so, then the coefficients of each coordinate will be 0 only if u, v, w are the independent coordinate. Otherwise it will not be the case. So suppose u, v, w are not the independent coordinate, then in that case a, b and c, one of this or all of three or two of this may not be 0, fine. But if u, v, w are the independent coordinate, then all a, b and c are 0. So this is a mathematical thing, I may derive it in the next video because this video will become lengthy, so I won't derive it. So let us see here. So our integration becomes like this. So this integration is not root pi because this is a normal Gaussian integration, but this minus infinity to plus infinity, minus infinity to plus infinity, this is also minus infinity to plus infinity. This v and w, these two integration diverges. Okay, so till now we saw a two-dimensional Gaussian integration like this. This formula we saw, e to the power minus x square plus y square plus 2 nu xy, and its value we get pi by under root 1 minus nu square. Fine. So this was a two-dimensional Gaussian integration. We also saw a three-dimensional Gaussian integration. So this is actually dx dy. So what is the value of this? We get pi to the power 3 by 2, 1 minus nu and square root 1 plus 2 nu. So we saw today these two Gaussian integration. One is two-dimensional and another is three-dimensional. We also saw shifted Gaussian integration for one dimension. So minus ax square plus bx dx minus infinity to plus infinity, and its value we got b square by 4a e to the power root pi by a. And we use this formula extensively to derive above two formula. We also use this formula minus ax square dx minus infinity to plus infinity, and its value is root pi by a. Sorry, this is a, correct. So this formula we derived in the last video, we derived it today, and these two-dimensional and three-dimensional formula we derived today. So right till now we have finished the Gaussian integration, and so this why we are learning this Gaussian integration, because in physics phenomena where you do the statistical analysis or some probabilistic analysis, you use this Gaussian integration very much. So if you make some probabilistic analysis and you propose some hypothesis, in that case you calculate this likelihood function for to test your hypothesis. In that case, this Gaussian integration is in very much used in physics research. So that's why we learnt here this Gaussian integration, and the next video will be on the Stirling formula. Fine. So if you want to know and learn about Stirling formula, please watch the next video. Fine. Thank you very much.